What inspires you most at SEGGER?
What inspires me most at SEGGER is knowing that everybody at least interacted with SEGGER technology once today without even noticing.
We are the embedded experts because we have a solution for every embedded problem.
You can see us as a tool provider for other people that also make products. So if you build a house, you need a hammer, you need a drill. We are that kind of company, but for software engineers.
Debug and trace probes, production tools, embedded software and software tools. Our vision is to simplify everyday life for engineers and end users.
People using these products are developers all over the world working with embedded systems. Our market-leading J-Link debug probe is the one piece of hardware that you will find on every embedded developer's desk.
SEGGER technology is inside everything. Space research, medicine, robotics, motorsports. You can find SEGGER everywhere.
With our technology, I hope we make people's lives better or easier.
My main motivation is seeing all these projects come to life and change the world or improve the world. SEGGER is the professional home for so many different people.
Developers, makers, engineers.
What unites us all are three words.
It simply works.
So, good morning and welcome to my talk, The Futility of Rigorous CPU Security Measures. So let's learn something about security. First, a little introduction about myself. My name is Nino Vidovic. I work at the SEGGER Microcontroller and I'm the product owner of the JTrace product group. If you want to connect with me on LinkedIn, you can use the QR code or just find me there. Also the coordinator of the SEGGER Educational Partnership Program. So if you're affiliated with universities or are a student yourself, you can also connect with me and we can maybe do cool projects together. And I'm also participating in the different software development tools that we also have that you see below there. So what will this talk be about? We will quickly learn about why we should do CPU security, what are the state-of-the-art solutions right now, what are the challenges after you have implemented these. We will show some different attack vectors, some strategies, how you can regain that control back, and then we will have a little conclusion. So let's start with why would we need CPU security at all? Well, the usual use case is you want to protect your IP somehow. Another form is, you want to defend your product in field from malicious attackers. So, for example, if you have some smart IoT device, you don't want your light bulbs to be used in some DDoS attacks without your knowledge because your name is on the line. Or you have regulatory norms that you have to fulfill where they just say, you have to do some level of CPU security. So I will now show some such use cases where you might need something like that. So, places where you have sensitive data that you're handling, like some cameras or smartwatches that are tracking health data, for example. Or you have you want to have tamper resistance for products that you want to either be aware of tamper attempts or you want to be able to disable the device if tamper attempts are detected. And also, you want to be able, for example, to differentiate between the tamper attack and an authorized access. So this is something that all can be solved with CPU security measures. Then we have authentication. So you have a client and a server side, and you want to make sure that the right client is talking to the right server, and there's no man in the middle there. So you need secure connections. Then we have things like trusted boot. So you only your trusted firmware, software, whatever is booting on the device. You might know that from laptops typically, but also you want to make sure that, again, your IoT, smart, whatever connected device only boots your firmware and not something else. Otherwise, bad things can happen. And of course, firmware updates, for example, over-the-air updates, you again have an external connection somewhere. And you need to somehow make sure that this is secured. We have this in cars now, and even like home appliances, like, you have to make sure that your smart home appliances can also be updated without breaking. So what is the state of the art here? First, about software a little bit. So I will just list a couple of examples. Like, there's a million types of strategies you can do. You can do software signatures, encryption, secure connection. I listed obfuscation. Obfuscation is not a security measure, but this slide is called state of the art, and many people think it is, so I will list it. But it's not a security measure. And below you see just an example of a software signature process that you can do, and then only your software would boot, for example. On hardware side, we have things like you can disable debug interfaces. We have, for example, at ARM, we have trust zone. We have temper protection. Usually the minimum is some kind of intrusion detection. We can have unique hardware keys that are already etched into the silicon. We can have secure bootloaders, which again, during silicon manufacturing, are already burned in and made sure that they have some kind of secure channels that on boot are available and stuff like that. And of course, the good old flash protection. And here in the picture, for example, see like a graphical attack of such, for example, against temper protection, where you can like encase your chip with like fake metal layers and stuff like that to make sure that your secrets from your chip design and stuff can't be easily extracted. So, we can do CPU security. So everything is great, right? Nothing can happen to us. It's fine. Well, then there's these challenges, right? Or I would say maybe challengers, right? Here's two examples of glitching attacks. On the right, you can even see from Benjamin. So if you haven't seen his talk, I think from last year or 2 years ago, he did one about glitching. He also published a nice blog article where essentially what glitching, for anybody who doesn't know what glitching is, what you do is you take the power supply of your microcontroller and try to turn it off and on for a short period of time. And the goal is to make sure that you produce a certain fault, and ideally the fault is you skip an instruction that would enable security, to keep it short, right? So if you now have all these beautiful security features on boot and you're like, nothing can touch me, well, if somebody gets hold of your hardware and can attack your power supply, then they will be able at some point to attack your firmware that way. So that's broken. So the next thing is more a non-intrusive way to just extract your complete chip design. So there's now research being done where they can, with a simple it's not simple, it's very complicated technology, but with essentially an X-ray, they can scan your chip 3D and down to like 10 nanometer resolution, and they just extract the whole chip design, and well, it's out there, right? So this can happen. And on the right, what you see there, that's not hair. That's a recent publishing from a guy who did a reverse engineering job on the Nintendo Switch Lite, where he wanted to reverse engineer the whole PCB of the Nintendo Switch board. And what he did, he removed all components. He soldered more than 2,000 flying wires to this and probed every single one of them to have a complete map of this 6 to 8 layer PCB. So even people go this type of lengths to get your stuff, right? So, who are these challengers? Well, some people call them hackers. We call them security researchers, right? Reverse engineers, cloners. So these are typically the challengers here. So looks broken, right? Well, it's not that bad. So let's maybe look at the different attack vectors in your typical engineering, embedded engineering supply cycle. So here you have something that goes like from a design phase, your development phase, production phase, and you have a shipping phase. So as always, any point is attackable. Like there's no illusion here. But what we saw is that once you launch your hardware, the attacker has basically infinite amount of time to attack your hardware, and they can put as much resources as they want against your hardware. So that starts here, right, on the shipping phase. But I didn't mark it red. I just said it's orange because we learned there are security measures that you can put in place, and I think this is more a question of business strategy. Like if you don't make back your money when you start shipping your product, you probably have a bad business idea, right? So because your whole cost has happened until here, and now you want to start make money, you have to do that at that point. And basically your security measures are just an annoyance or hindrance to give you more time to gain back your investment. So the right side is like silicon vendors try to make more features and stuff. So the right side is, let's say, solved, attackable, but solved, right? So yeah, what about the left side? So what about this part here? Well, this is what usually is done in-house in some way, or is in some way secured due by some secure processes that you have established that are proven over centuries or decades, centuries not, but and you can mitigate many attack vectors there, and that's what usually is considered the safe haven or trusted environment where we usually work in, right? We develop our stuff, we test our stuff, it's tested on our machines and then servers, and everything is great. But there's this in-between area, right? So, and up until this point, typically you have already spent like 90% of your investment. Like all your money is in this project. You have spent all this time to get the security features, so the right-hand side is not so much attackable and stuff like that. But what about this production, this gray area? And if you don't do it in-house, and many do it with contract manufacturers, this could be a problem. So why is this a problem? This is how a production typically looks like. So you have some kind of data delivery to your production PC. You have some interface to a programming tool and some interface to a target device. These interfaces are oftentimes open and very well documented, so you can sniff them. And if this is containing a binary, you're in trouble. And let's remember what you give your production company. You give them your BOM, your Gerber files, schematics, materials, everything, keys, like they get everything, right? So you give them a blueprint on how to make exact functioning clones of your hardware. And we have seen, for example, the data delivery part. We have seen like things like where people send their secure firmware via email attachment, right? So you don't want really to do that. So yeah, the question is like, how much do you trust this environment where you send this data to? And yeah, essentially every step here has the potential to extract your secret, your IP, your binary, your secure keys, and whatever. So how can we get that control back? Well, we just secure every of these interfaces, right? It's simple. Well, as said, it's a little bit a problem, because how do we actually do that? Because USB, Ethernet, RS-222 is pretty well established, and SWD, JTAG, like you can sniff this stuff, right? So, how do you make sure this like ideally end-to-end encrypted, right? And here we have a solution with Flasher Secure and TELP. So let's quickly delve into what a flasher is. It's this blue box. You guys probably know us from our J-Links or the debug probes. At some point in time, people realized that with J-Links you can program chips very fast, and they liked it and started using them in production. But then they realized that their production environments need different interfaces, need need to dump it down. You need a program button you can press and stuff like that. So we had to make this guy. But then people realized, wait a second, all our firmware and secrets are now at this contract manufacturer, and it turns out that more products of our PCB is being produced and then landing up on the market than we have ordered. That's not cool. So we made this one. What's the difference? Well, first of all, it's red. So, but yeah, this one on top of the features that you saw before, you get authorized production, authenticated production, product volume control, security, up to the flasher and beyond. And I'll talk about these points in the next slides. So how do you authenticate what is being produced? So how you make sure that things like your first pass yield, your quota, your reprogramming attempts are all logged and you can act on them. Well, the process is here shown. So we do identify the target somehow. So here's it's some washing machine or whatever. It has some kind of unique identifier. We check in the database in your trusted environment. The flash secure is connected via Ethernet to the internet over secure channel. And then we have your trusted server within your trusted environment zone that we saw in the process diagram. And this server now decides, has this device already been programmed? Am I allowed to reprogram that device and stuff like that? So you can make constraints there. And if any of these constraints gets tripped, you get a warning and you can talk to a contract manufacturer and ask them what is going on. Why are you having 20% failure rates? Where do these boards go? And stuff like that. So what then happens when the authorization is given, we sign the firmware, and this gets sent over triple layer secure channel to the flash secure, and gets unpacked and encrypted there and programmed to the target device. So looks cool. You can now track what your production is doing and act on anomalies, right? But again, this only solves that part, right? So we can now we skip the production PC, we send the encrypted image directly to the programming tool. You cannot sniff anything here. If you attack the programming tool, this is also detectable by us. So what's left is the target side, right? So we have this interface. So how do we do that? That's what we call TALP. It's target encrypted link package. And the idea is to have something that works with every production environment, because we did not invent secure production. This has been done before, but in very custom and unique ways, let's say. And sometimes it's very over-engineered and sometimes not that secure when they leave their certain gaps in their whole process. And again, like what's the point if you have all the security measures that you put in place, if you have sent someone just to a binary and he can make just clones just before you start making money. So let's talk about TALP. So it starts like this. Again, it's very similar to what we saw before, because we again have to authenticate the target we're programming. So again, we read the UID and do the same things as before. Now we transmit the image after the permission to the flasher again. And the whole channel is wrapped with HTTPS. This is wrapped with another TLS layer, and the binary itself is encrypted. So we have 3 secure layers on top of each other. So even if you are open to open one of them, for example, sometimes firewalls will try to open the first HTTP layer. This is also something that you will then know about, and then you can also again call your contract manufacturer's IT and ask them, why the hell are you doing this? So this is what's doable. And then when this is established, the next part is in plain text. We first install bootloader to the target device. And what this now does is over Diffie-Hellman, we try to get a secure key exchange between Flash Secure and the target device. And we then cut off the standard debug interface that is open, public, and very easy sniffable, and exchange it over proprietary secured channel with the new key that we have made the handshake on. So after this handshake is completed, we can now send in over this interface. We call it an agent software, and what this does is it goes onto your target device and checks if everything is as expected. Has anybody tampered with the device? Are the timings still as expected? So we try to find out, has at some point during this key exchange or at some point before somebody tried to manipulate your production here. If that's not the case, that's great. Then we can now start programming the encrypted firmware image, put it on there. The secure bootloader that we put on there before can unencrypt the image chunkwise on the fly, and then once everything is finished, which is step 6 now, we have now programmed the device fully. There's no residue or leftover from the secure stuff that we did before. It's just your image now. And we cut off this proprietary interface here and reset the device. And from step 7 on, your device is on its own, and it's doing this what you would have done without the secure stuff before, right? So we have reached a whole closed loop system where from your unit testing development server or whatever, where you have a trusted environment, you've extended this now to some third-party offshore right to the target device. So where does this leave us? So let's summarize again. So yeah, we have this whole chain again, and as we saw, everything is attackable. We know that the right side is it's a cat and mouse game, right? So somebody invents new security measures, we implement it, somebody breaks it, and stuff like that. So it's a back and forth, but it's a battle, and sometimes we are winning, sometimes the bad guys, whoever the good and bad guys in this story are, I don't know. But left side is also kind of solved due to processes, NDAs, your IT processes and stuff like that. So, but as we saw, the gap, the production, this is what many people simply don't have on their mind, and you have now spent so much money and time, and everybody knows how annoying it can be to implement the security features. And yeah, to leave this gap can become costly. So yeah, what's the solution? Where of course there's no perfect solution, but with for example Flash Secure and TELP, you have a pretty universal way that you can always apply to any target CPU, where you can close this gap, and you only have now to worry about the shipped product essentially, which is on its own and has to protect itself and fight on its own against attackers. And again, to circle back to my initial title of this talk, so what's the point of implementing all of this if you just give your secrets away to somebody else? And this is, I think, a cool solution to this. And yeah, I'm already at the end of my talk, so thank you for your attention. I hope this was interesting. Are there any questions? I will try to answer most of them. If I can't answer them, I've brought my product manager back then, Peter. Let's see how this goes.
First of all, thank you. That's a very interesting topic, I think. 2 questions regarding the 2 communication points, so to say. So first off, how do you ensure that, how do you authenticate the connector against the server? So how do you ensure that no one just writes a script that connects to your server, tells the server I am a flasher, and downloads the image?
I see. Peter knows. But like we have like again, every flasher will have unique identifiers, and we will be able to authenticate against the server, which we saw as one of the security measures. But yeah, Peter,
please come to our booth. we talk about it in detail because I think we have no time left on the schedule, and we can dive deep into the detail if you want to know.
All right, next question. Yeah.
Follow?
Okay. So if I understood that right, basically this requires the flasher to have constant internet access?
Yeah.
Okay.
Like you can... Like if you want to have the monitoring capabilities, right? We can of course do this also in air-gapped systems, but then you lose control of some of the monitoring features. So it's again a trade-off, right? So I would not recommend it.
The second question would be for the communication to the device itself.
Yeah.
So you say you protect the image, sending it to the chip by sending a bootloader first, that then decrypts the image.
Yeah.
So if an attacker has access to this connection, what's preventing him from just downloading the bootloader and the encrypted image and fishing for the key in the bootloader?
We the key exchange via Diffie-Hellman makes sure that you can, over an unencrypted interface, you can negotiate a secure key.
Because every key.
Yes, you send parts of part of the key negotiation, and every site then comes to the same private key without ever exposing the secret. So there's this beautiful slide from the Wikipedia article from Diffie-Hellman, which essentially shows this in with colors, and I like that very much because it essentially shows how this works. So and then the other channels that we open is just a serial connection. That's it. It's not magic, but it's secured with the key that we negotiate here. So you can't look at the it's garbage data for somebody sniffing. Yeah, and then due to this process, the key cannot be extracted just by either extracting the bootloader or only extracting the plain text transfer of the bootloader or stuff like that.
So one question regarding the update process. In the last step, you have shown that you disconnect the device and then the firmware gets decrypted and installed. So it can't be decrypted on the fly because...
No, it's maybe I have to set this wrong. So we'll have... it's this one. Yeah. It's being programmed chunk-wise because we still have this whole secure stuff installed, right? So we have to... do it chunk-wise, and it's being programmed on the fly. We disconnect afterwards after the whole image was installed, and we have overwritten all the secure stuff that was monitoring everything.
Okay, so how does it increase flashing time, if at all?
I don't have numbers for that. I mean, you obviously have the flash programming is as fast as you would have done it without it, right? We still are pushing the limits of the flash controller here, but you obviously have all these exchange steps before and after, and so it probably adds a couple of milliseconds or something. But it's I think if you think about it in a production environment, you have this test needle stuff, and you have to put it down. So the whole production process is 10 plus seconds per board. So adding a couple of milliseconds or maybe 100 milliseconds, it's worth the added security maybe. And Peter wants to say something to this. Maybe I'm completely wrong. Let's find out. Yeah, or look at detailed information at our booth.
All right, then thank you very much, Nino.
All right.